Hello, everyone. It's me again. Welcome back to the winter term of Causality. Today it's already the 5th session. Wow. Last week you had Jonas and Moritz heading the sessions. So I guess most of you have been there. I mean, it's the more or less usual crowd. I hope you had fun. We were talking about, causal discovery and all these kind of things. But today it's another major part of causation, which is identification, right? So we have seen discovery, where we have more this machine learning type of perspective, where we're saying, okay, we want to learn these relations, we want to learn these representations from data, purely data driven. But actually, this might arguably be the more causal thing to do, because Perl envisioned this framework as a formalization, essentially, of cause and effect, and therefore these conceptions of interventions and counterfactuals. And in identification, what we are trying to do is, in principle, in theory, given our assumption, formalize and find out how we can express, certain causal quantities in terms of non-causal quantities. Why? Because non-causal quantities are the ones we usually have, right? So this is the other big strand. This one is more concerned with assumptions and what can we do with these assumptions. So how can we make sound inference, something you define in logic, for instance, whereas the other thing is more concerned with, well, learning these relations in the first place, learning these assumptions that we talk about, justifying these assumptions, right? So they are both, in a sense, equally important, and actually they contribute to each other. And today we are seeing this other one. So a brief overview of today's session. We're just going to do a brief recap of some of the important concepts that we are going to use in today's lecture. And then we are really just having 2 sections. The first one is we are really going to talk about what does it really mean to identify? What do we mean by this word, right? And what are the concepts related to it? This is like the problem phrasing, right? And then we are actually going to talk about how we tackle this problem in section 2, which is now called Tools for Causal Identification, which is going to present all the different ways, or at least major ways of actually dealing with this problem of identification. As always, if there's any questions or thoughts, impressions, right, intermediate, feel free to just butt in. And we're going to cover also some example calculations, as you saw, for example, in the 3rd lecture, where we talked about the causal hierarchy and interventions and counterfactuals. So let's jump right into it. So section 0, a brief recap. So all the crucial and important concepts for today's lecture. So the graphical stuff from last time, but also, the concept of interventions and so on. So, but first, the central topic, right, of Perl's formalism, the structural causal model, M, which we also know as the data generating process. It's the king beyond, the joint probability distribution, because it generates all those. It's just specified as this tuple of endogenous, exogenous variables, which are mechanistically related by these functions in the set F. And then also we have some stochasticity, because usually we don't know anything about these nature terms, about these exogenous terms, so we have probability distribution on that as well. And typically what we assume M is recursive, so we can compute it easily. It's essentially a cyclic, right? Now, as I said, SCMs generate data, and for example, this is the one, if you remember from the very first session that we had together, this was the motivation from Peter Sedan's book, where you have, activity of some gene and a phenotype, and all these data points are actually generated by the SCM, right? In this case, the non-causal L1, as we have established, L2 and L3, so interventions and counterfactuals, these are the causal things. There is some change happening there, whereas in L1, it's just a stationary, the static thing, and that's non-causal. And you can get quantities like this using Bayes' rule and probability theory. For example, what is the probability of y being small y if x is small x? Now, an important concept is that of intervention. So we can modify SCMs. So again, if we have an SCM here now, specified actually, so we have 2 variables x and y. We say we have these 3 exogenous terms, so ux, uy, and then uxy, which is going to be a shared one. We have a probability distribution, which is not specified here, but it could be some I don't know, Gaussian noise. And then the structural equations could be something like this. X is just generated by 2 of the exogenous terms, and y actually additionally takes x as an input. If we look at, for example, these distributions, we clearly see a difference here. I mean, I'm not showing any numbers here, but in principle, what we have is that, knowing x, because, it's a cause actually of y, will actually help in predicting y. And so it's not the equal thing to just P of y. Now, if we do an intervention, which we can denote typically by this do operation, right? We have seen this response variable thing, but this potential outcome kind of view, and it's the more general view. But if we just talk, about interventions, about purely L2, then we can write this, for instance. And what this really means is we just put the substrate x here and replace within the structural equations the one which is dictating x with little x, right? So we are just hardly pushing it to some value. And everything else remains the same. So it's like a really local change. And then we also see again that this quantity generally is also obviously different, because if I change x actively, that's also going to induce some change in y, because again, it's an argument, right? You see it's little x here. Again, nothing we have not seen before. It's just a quick recap. Now, SCMs also induce causal graphs. This was hinted before in the first 3 lectures, but really discussed only in the last lecture. So again, we have our structural causal model. Typically, this is latent, right? That's why we usually also talk about causal graph, because we don't observe the SCM. We might not even observe the graph, but we try to learn the graph where we assume at least something about the graph. Assuming something about the SCM might be a lot more tricky. And now here we have, for example, 3 variables. You see that y is being caused by x, and that is independent. And you could actually depict it as this kind of graph. So if you look closely, I put the star here to indicate that we have an ADMG here. So far we have talked mostly about the directed acyclic graphs, but we have also had some hints in the last lecture that there's these mixed graph because, well, we have these bidirected dashed edges here. Whether they are dashed or not, it's not so important. That's more a stylistic choice. But they are bidirected edges indicating that there is a confounder, actually. There's a common cause somewhere in between. And this actually comes from these U terms, which are being shared, right? Yeah, and when we write, for example, something like G of M, that's simply the graph which is actually implied by the underlying structural causal model. So again, this thing is also just like a DAG, just that it has these extra edges, which denote that there's some variables you actually don't know of, which cause some other variables. And in this case, X and Z, for example, are caused by some third variable and Z and Y. How do we actually construct this graph, right? I mean, it's very intuitive. Here it's just written out, right? So you have your SCM, and then you said that the G that you get from this SCM, written G of M, is a causal diagram of that M if it satisfies these 3 things. And it's essentially for every endogenous variable in the set, we add a vertex, so we have a node. Then we add an edge between the nodes if one which precedes is part of the argument. So for example, x is being caused by y. So y is part of the functional equation f. And so we draw an edge from y to x. And then thirdly, for the bidirected edges in this case, you add a bidirected edge if any of the 2 conditions is set that for the 2 where you want to add the edge, there are U terms which are either correlated or they are actually shared, right? So if you just go back for a second, for example, you see here this should actually be a UXZ here, but then you would actually have these shared arguments. Here it's just denoted as those ones being correlated, but you could write it also in the way that they are just part of the same function. Yeah, and that was essentially just a brief recap. Any questions so far or any thoughts? Anything which was unclear? Yes.
Could you go back to the again, the last with the equations. So could their share be UXZ?
Yes, either they share or they are correlated, right?
But correlated in which sense?
That the U's are correlated, okay. That the noise distributions are correlated.
But yeah. We assume didn't we assume they are independent?
That's when you have a Markovian thing. Okay, exactly. But if it's not Markovian, okay. Then, but now you're spoiling a little bit, which is what is called. Yeah. So.
Yeah, but you stated that.
Yes, no. This is what we did before, right? Like typically we say, it's recursive, which is semi-Markovian, which actually includes this class, right? But then, if you actually if you factorize, if you make them independent, then it's actually Markovian, right? So these will be naturally non-Markovian, but we are going to see this again. But yeah, good catch. Thinking. Okay, cool. Good. Yeah, now the first section actually of today's lecture. So what does it really mean to identify? So we're going to define what causal effects are, right? And the problem of estimating those causal effects, right? Or even not just estimating, but just in general being able to write down an estimate of what in theory should estimate your causal effect. So in layman terms, work with what we have. Okay, so what is a causal effect? I mean, things of these, so as Tim was just pointing out as well, I mean, a lot of these things you can also, if you're thinking ahead, you know, a little bit, you can make the connections. So some of these things are less new, right? If you come from that perspective, but we are going to do it rigorously now. So because now we're in the lecture, we were talking about identification, causal effects are the central topic, right? So we boil it down, right? Okay, so a causal effect of some variable or sets of variable x on some other set of variables y is a function from x to the space of probability distributions on on y. So what it's really saying is that, you know, you have these generative models, right? So just like a conditional distribution, right, is a function of your x in this case, it's the same for the interventions. So we change x, right? And depending on how we change, we get different distributions over the y's, right? Like we judge y differently, we believe about this y differently. Again, remember, this is just syntactic, right? If it's purely L2, we typically write 2, but, you know, we could have just used this shorthand here, right? Which would mean the same thing in this case. How do we make sense of this name? So we are saying that this is the causal effect. This is also oftentimes called the causal mechanism, right? Because this is the thing which usually stays invariant through, say you have multiple environments and you're changing always once in a time your x in a certain way. Generally, this mechanism of how, you know, x is generating the y stays the same, right? In physics, this would be, for example, you know, you're climbing up a mountain, the temperature drops, right, with the altitude, and essentially this is captured by this thing, right? Like what is my belief about the temperature if, you know, I increase the altitude? But now, how can we make more sense of this? Like, how can we justify this more? Like, giving it really the meaning of causal effect, right? So, of course, the causal part, you know, we are changing things, right? And we are always observing something with respect to a change. And so that's a crucial quantity, right? Or property, actually. And so typically we have that, right? Like we have that there is a difference. So there will exist some kind of intervention that I can do such that my belief about y changes about what I would have believed if I hadn't done the intervention, right? So this equation here is really just telling you I changed something and there's some change to be observed, right? If there's no change to be observed, I still change the system and it might still be causal, right? But it makes more sense to justify this way because there is actually a change you can observe, right? Because if you cannot observe it, it's just like the ferry example we had in the third lecture, right? Where we just said like, okay, you know, let's assume they are indetectable, you know, invisible ferries, right? Because they're indetectable, you will never know, but that doesn't mean you should conclude they don't exist, right? It will be the same thing, right? So this thing is really just justifying why we call it a causal effect. However, you can also justify it in different ways, right? For example, we have seen just now that you can say that, you know, if I do an intervention, there will be some kind of change. But you can also say that if there's, you know, different types of interventions and there's some change between those, that's the same thing actually, right? I mean, a special case of this would just be setting it to the empty set, essentially, to a non-intervention. And then you would have the first property, so it's easy to see, right? But this is more general, actually. It kind of makes sense, right? Like if you give someone treatment A, treatment B, right, and you observe differences, then you would say, oh, there's a causal effect actually from my treatment. Another way actually of doing this, which is less related to these other ones, but also equivalent, is that, you know, if my x and y are actually dependent in an intervention where the intervention is actually just random, then I also know that it's a causal effect. People who have, you know, studied maybe a little bit of econometrics before, right, and these related topics, they will recognize this essentially as this randomized controlled trial, right? So in a randomized controlled trial, what I'm doing is, you know, I have a population and I'm choosing within the population randomly who's getting the treatment and who not. Say I want to discover, you know, the effect of a certain drug on people. I have all kinds of different people. They have all different characteristics, right? And so what I do is I don't choose based on any characteristic or anything. I just purely randomly try to assign anyone, you know, a treatment, non-treatment, right? Like the drug or a placebo, for instance. And then I can actually measure the proper causal effect, right? Because, well, there's nothing for it to depend anymore. It was completely random how it was chosen that they are administered the drug, right? And this is exactly what's happening here. So if this is a random intervention and you see that there is a dependence between them, then you can be sure there's a causal effect, right? So these are the different ways we can actually justify the meaning of, you know, py to x actually being a causal effect. You can derive, you know, all kinds of interesting quantities from these things. Here's a very basic and maybe also the most popular one. So we say that any quantity q which is derived from this generative model, from this causal mechanism, this causal effect, that tells us how much y changes due to this intervention. This is, well, a derivative of a causal effect, and itself also a causal effect. And one example could be, for example, say you have variables x and y. X could be now a binary variable indicating whether someone gets a drug or not. 0 is no drug, 1 is one drug. And then we define the quantity as this. We just say it's the expectation of y if we give the person the drug minus the expectation of y if we don't give the drug. Say y is representing on some scale. It could also be binary. It could be continuous, whatever. How much a person might recover, right? Then this difference is telling you essentially that when you give the drug, how much will they recover? Will it be better or will it be worse, right? And that's why we typically call this thing the average treatment effect, right? It's a thing which is really derived from these things, right? Because if you use this thing, you can compute these expectations, as you can see here again the formula, and so this is indeed a causal effect, a specialized causal effect, which we call the average treatment effect. So now we have seen what a causal effect is, but what does it mean to identify causal effects? Before we talk about, how we actually identify them, we need to define, what it means for a causal effect to be identifiable, right? Like, what does it mean for a causal effect to be searchable? How can you find it actually, right? Like, which ones can you actually find? So a very principled way of formulating the problem class, essentially. And so we say that a causal effect, right, something like the py to x, as we have seen now, for some treatment variables x and some outcome variable y, these treatment outcome, it's just for the sake of the example, you can ignore this for now, right? You're just treating one as, the target and the other as the thing which is going to be changed. We say that this causal effect is identifiable from these two things. I've put input here for the more computer science view, right? So really see it as something you feed into your program. In this case, your identification solution program. From a causal diagram G, right? So we have the causal graph, or assume something, and the observational distribution over your variables V of the SEM. If the causal effect, right, the interventional distribution, is uniquely computable. So that is what it means for it to be identifiable. Essentially, I have some, insight, whether it's learned, it's assumed known of G and about these observational densities. And if I can compute this uniquely from those, then the effect is said to be identifiable. Why do we even define this very basic notion? Because you're going to see not everything is actually identifiable. There's also a different way of seeing what I just said, right? Like giving it some intuition. Looks like a bit of a complicated schematic illustration here, but we're going to dissect it one by one. So let's start in the upper left corner. So this omega star is now going to be the space of all SEMs. I mean, this thing you cannot hope to compute, not know anything. It's a crazy thing, right? Like we have seen these SEM, these small things, but SEMs can be large, right? Like if we assume that, nature is generated by some sort of SEM, any of these single points could be ridiculous. And any other point could just be maybe a false SEM, which is still an SEM. It's not the one which our nature uses, but whatever, right? But also all the examples we have seen so far, of the coin flipping, of this, of that, right? Like all of them are in this space, right? Like this is beyond infinity, right? And let's say we take now 2 points, some two SEMs, and we look at what they have in common, right? For example, they can have in common the observational distribution, right? So they are defined on the same set of variables, right? For example, they talk about, coin flips, but not just that, they actually have the same parameters up to the extent that if you just look at the observational distribution, they're going to be the same, right? So this is the thing. Now, additionally, because we said in identification, we have the observational distribution, but we also have the graph, they will have the same graph even, right? So M1 and M2, they have the same observational and the same graph, right? So they imply the same structure also on the variables that they have in common. Now, identification is the question whether, they also agree on the second rank, on L2, on the interventions, right? And essentially what our definition now is saying that every time this picture is actually fulfilled, right? So for all the pairs which agree on this and agree on this, if they also agree on this, then the effect is identifiable, right? Because that is what we mean by uniquely computable. If they would disagree here, so if here we had 2 different points, but everything else was the same, then there's no unique computation, right? Because you would use this and you would use this, but you could end up on either of those points. It would not be unique. So there's two different causal effects essentially. But if you have this picture where everything coincides, that's what it means for an effect to be identifiable. This is going to be, I guess, a little bit hard to grasp for the first time. We are going to see some examples. We are going to develop more intuition, right? Again, we can, discuss also after the lecture, no worries. But this is really what we mean when we say, causal effects identifiable, right? To help, digest this a little bit better, there's these Venn diagrams, again, a set view, right? But now just with colors. And so here we have two boxes, which represent, SEMs. And one of them is identifiable. So the ones which satisfy the property we just discussed, right? And one is non-identifiable. So all the models are just in the gray box. Now the blue circle are all the models which have, the same graph. Yellow is all the models which have the same, observational distribution. Now the intersection are the one where the causal effect is also the same. And so it's identifiable. But for the non-identifiable, there exist some, right? Some pairs of SEMs which will never agree on this thing, right? Now you might ask, well, why is this the case? Well, very simple, because actually Tim was already pointing at this earlier, possibly not knowingly, yeah, but essentially we have the semi-Markovian SEM, right? So we have this graph view now, which is based on the things you have seen with Moritz and Jonas last time. So here we depict the augmented graph. So I have the little a here as a subscript for augmentation, which is really just adding the exogenous terms. Here in gray notes extra, right? So typically we have seen always written, x1 cos x2, and that would be the whole causal graph. But now we are showing the full picture. So we also draw the exogenous, the U terms. Here they are now denoted by E for exogenous, right? But this is also just to, make you a little bit more comfortable with the fact that, they use all kinds of, so some people use the U, some people use the E, some people use the N. It's all the same thing, right? You got to learn this. And so here we depict those, right? And this is semi-Markovian, right? Why? Well, because essentially we have here this confounder. So in the U's, we have these confounders. And what this really tells you as well is that, the PU is actually not factorizing, right? Another view of seeing this would be essentially that these could be two variables actually. So say E3 and E4 pointing to both of those, and then those are correlated, right? So it's not independent, right? This is a different way. So you can actually summarize these noise terms because anyhow, they are just distributions. And yeah, this thing is semi-Markovian, right? And in this thing, actually, it's one of those which is non-identifiable, right? So if you have something like this, right? It's the effect. So you'll have models which agree on this graph, right? On the x1, x2, they'll agree on the observational. But because there's some, spurious association flowing over E3, you essentially have non-identifiability, right? This is what's happening. In the moment you become Markovian, this thing drops out, right? You don't have any of those anymore. So it's very clean. If now two models agree, then they will necessarily also agree on the causal effect. Why? Because, well, there is no spurious association anymore between those variables. So essentially, these Markovian SEMs, why do we like them? Because they're actually a very special subclass of SEMs. So if, PU factorizes, as Tim was saying earlier, then, these U terms are independent, which is just another way of saying that there are no hidden confounders. And, we all know, even if you don't know causality, having no hidden confounders is a good thing, right? And there's this fundamental theorem, which essentially tells you, we're not going to prove this now. I can give you the references if you want to, but any causal effect in these models is actually identifiable. And that's a very strong result. So what it's telling you is that this class that we were looking at, this intersection where we have all the SEM pairs which agree on graph observation will always actually also agree on the causal effect. You can actually not construct some SEM pair where this would not be the case. The only way to get this would be to actually introduce some dependence between the U, like introduce some hidden confounders, right? So as soon as there's nothing hidden in your system, you can always identify the effect. And that's actually a super strong result for causality. Yeah, we gotta get these XKCD comics back again. So here's one of the number 326, effect and effect. We see a person sitting at their computer, and well, it's their hobby. And what's their hobby? Using the more obscure meanings of effect and effect to try to tip up amateur grammar Nazis, right? Like, there's also, classes of grammar Nazis, not just, pros, there's also amateurs. And well, I think that our foreign policy affects the situation. As someone saying here, and well, the grammar Nazi is saying, you mean affects, right? It's affecting the situation. So essentially, what we have seen now is what we mean by the definition of an effect, right? That's why I've put this comic here. So the effect actually has a very concrete meaning, and we have seen now what it means, right? And even if it still seems a little bit clouded and abstract, the more you hear about this, the more you see different perspectives, the easier you're going to understand what it is. So before we move on to how we identify and actually do this in practice, I want to clarify a little bit more on the terminology on an intuitive level. So the first one is going to be identifiability versus identification, right? So someone who sees this for the first time, they might be tempted to conclude that this is the same thing, that's just like English, the same words. No, we have just seen affects and effects as very different words, right? We can have very subtle change in the way we write a word, and it can mean something very different, right? And this is the same for these things. So it's very important that you grasp this. So the condition that we saw that these causal effects are uniquely computable is what we call identifiability, right? And our theory tells us, that it is possible to uniquely determine those, and we have seen Markovian STM for all of those; they're always identifiable. But the process of identification is actually that proving, when you have your graph and you have your observational, that whatever you have given now as your solution is actually the solution to it, right? So you're going to see some examples on this, but this is the difference. So identifiability is just, in principle, can we do it? Is it possible? And identification is then actually the process of getting this expression which solves it, right? And actually proving that it is the expression, right? Now, there's still a difference to estimation. So if you compare now identification with estimation, estimation is actually taking this solution, which we call the estimand, and estimate it with the data that we have at hand. So the densities that we talk about, at first they are just algebraic expressions. They are just the symbols, right? And the estimand is again also just a bunch of symbols, right? But these symbols have a meaning in that they are actually probability distributions, which we can estimate from data. And now proper estimation is taking this estimand and using your data, and this is typically done by machine learning, of course, and get the estimate. So to summarize those three terms here in an example, so let's say we want this causal effect. This is what we seek. And let's say we assume that, we have access to P, X, Y, Z, and also to a graph that looks like this. There's no relation between X and Y, but there's there should actually also be an arrow from X to Y. This is an arrow. But there's a common cause, a confounder Z. And again, these are assumed, they are not given, right? Like these are not objects in the sense that we have, right? We are just assuming them. Now, this year, you are going to see where this formula comes from in the second section, but just bear with me for the moment. This formula is true. So we have an equality on the algebraic level here. And this right-hand side, we call the estimand now. This is the product of the identification. And now here you see, I've just replaced the P's here with Q's. Why? Because these Q's now actually represent our estimate of the estimand using our data. So here we have X, Y, Z, n data samples of X, Y, Z. And we estimated Q, which should be an approximation to Px, Y, Z. And Px, Y, Z is an infinite object. It's a theoretical object that we're never going to have, right? But that's why we have to differentiate between those, right? So these are theoretical objects essentially. I mean, the graph, you can argue you have that, but the Px, Y, Z you never have. This is like an asymptotic limit, right? This is just an expression here. And now you can form this estimate where you identify the causal effect just based on these two things. So you have this. From this you can derive these two things. And given the graph structure, you know that this is going to be the equality. And now you use the data to estimate those p's, right? That's essentially the big picture here. And talking about big pictures, just visually once more, you are given a query, right? So your causal estimate, you have some constraints, right? Some kind of graph. You have some kind of data, which will give you the possibility to approximate these densities. And now you have whatever kind of algorithm, you know, and we're going to see different algorithms essentially. And then it gives you a solution. In the case of Markovian SEM, everything is identifiable. So they will, if your algorithm is powerful enough, if it's complete, you will always get a solution. And then the solution is going to look like this. On the left-hand side, you will have interventional counterfactual distributions. And on the right-hand side, you will have something purely statistical, purely L1, purely non-causal, but just based on your data. And why does it work? I mean, we saw in the third lecture that, you know, in principle, it's impossible to jump in between if you don't do the interventions actually. Well, it's possible because this is what you assume. If you choose to, you know, have different assumptions about your data generating process, then this formula will look very different. And if this formula looks very different, the numbers are very different. So your conclusions are very different. So essentially, we can do identification because we make assumptions about the graph, right? And then, you know, using our inference engine, we actually get something with what we can work with. And now, how are we going to solve this? This is the main bulk now of today's lecture. So we are going to talk about 3 different approaches to identification. We are going to, you know, discuss general Markovian models, the heuristic class, which is very nice. We're going to talk about some, you know, certain special graphs. But then we're also going to talk about general SEMs, so even non-Markovian SEMs. And these 3 techniques we are going to discuss: truncated factorization, adjustment sets, and the celebrated do calculus by Pearl. So let's take a little moment to, you know, breathe in, hey, Christian. And yeah, let's reflect for a second. So, yes.
Questions about the estimates and estimation.
Yes.
I was thinking if at some point is or are the cues there about estimation of the
densities.
probabilities?
Correct.
There are no estimators, or is there?
Yes. So you're.
I was thinking about is there an estimator missing?
Yes. The estimator would be your machine learning model, right? Okay. So for example, it could be like a sum product network, it could be a neural network, it could be whatever you want, right? Obviously, some kind of probabilistic model makes a lot more sense because these are probabilistic tasks, right? Probability theory learning tasks. And yeah, you use your estimator with your data to get the estimate for the estimand,
I see.
Which is the solution to the identification, which stems from the identifiability. And so now we have all the terms in here. Yeah. So anyone else? I think
Can you prove that then SCM is Markovian? Or like, would you just do that by saying the noise terms that I modeled are noise? Like, I don't know.
So see, that's the thing. So in the last lecture with Jonas and Moritz, you saw causal discovery, which is all about using data to finding at least the graph structure. The graph structure includes the nodes, right? And the relations between the nodes. That's a thing where hidden confounders can be. So that's a thing of the question of Markovianity, right? And well, if your causal discovery algorithm can prove it, then yes. Now, that's just rephrasing your question. Can any causal discovery algorithm prove it? We have algorithms which can give you, which are complete even for hidden confounders, for example, the fast causal inference algorithm. However, there's some other assumptions you have to make which you are not happy with, maybe, for example, faithfulness and whatnot, and so on. And so it's, again, just rephrasing your question to whether I have these other assumptions, which is why ultimately I would be inclined to say, no, we don't have a general purpose scheme to proving this. And that's why Yuda and everyone else is talking about all of this as a way of talking about your modeling assumptions, right? Like, this is not about whether my modeling assumptions are true necessarily, but about whether, you know, I can actually talk about them in the first place, right? So I talk about them, and now I justify why I believe they should hold true, right? And that's my proof. In a sense, it's very similar to the foundations of logic, right? If you talk about, you know, base axiomatizations of all our mathematical results, you know, you look at something like, I don't, Semelo-Frenkel's set theory, you know, and then there's a bunch of axioms, maybe even the axiom of choice, and, you know, you have to justify that, right? But is there a definite way of proving it? No. So that's the comparison I draw now. But yeah, very important, very fundamental question. Anyone else? Good. If not, then we are going to move on now to the main bulk of today's lecture, which is section 2, the final section, which is, however, divided into subsections according to the 3 methods I've just mentioned now for these different cases of SCMs. So these are going to be all tools for actually solving the problem that we just defined, right? And again, it's going to be adjustment sets, truncated factorization, Purdue calculus, and optimization, which I didn't mention on the previous slide. You're going to see why, actually, because it's not proper identification, but we'll get to that. So let's start with an example again, as always. So this is an example we have encountered also in, I guess, even the very first lecture we had on the motivational part. So let's say we have these 3 variables, T, Z, and R. Z is the size of a kidney stone a patient has. T is the treatment that the patient is going to get, and naturally it depends on the size of the kidney stone. You know, a doctor will monitor them, and, you know, if it's a large kidney stone, it might be, you know, in need of a certain kind of treatment, so it's definitely dependent. Then there's the recovery, which depends on both. Obviously, a bigger kidney stone is more problematic, so, you know, it'll have an influence, but also the treatment that you get will obviously have an influence. So this is the causal graph we get, and again, any kind of tuple that we get, Z, T, and R, it's going to be a kind of class of patients which are described by the same values on here. Now, I want to briefly talk about Simpson's paradox once more, right? Because this is going to relate to all of these topics which are to come now. So in Simpson's paradox, we have a very weird situation. What is happening? So at first, we have, you know, 2 treatments. For example, you know, this open surgery, and I don't know if anyone can pronounce this for me, but this other treatment, treatment B. And we see, you know, we have patients, we have 350 patients, 700 patients, and we see that, you know, we have a certain set which gets treatment A, a certain set which gets treatment B, and treatment B, so this score is indicating the recovery, right? So it's like R being equal to 1, that a patient recovers from the, you know, kidney stone problem. It's actually, for the treatment A, is actually lower than for B. So here, as we've seen in previous lectures, we'd be tempted to think, oh, treatment B is somehow superior. But where does the paradox now kick in? Well, if you actually look closely, if you look into the subgroups of, you know, people who actually have, you know, small stones and large stones, then you see the reverse picture. And that's the paradoxical thing, right? Because it would be tempting to have the reverse conclusion now. So essentially, whether you have, you know, large or small kidney stones, in both cases, treatment A is having higher chances of recovery. But as we have seen in our lecture also, you know, on the causal hierarchy, and where we discussed, you know, the difference between interventions and kind of and conditions, the causal effect actually disagrees. It agrees with these sub-effects, which disagree with the original statement, right? So if we actually give someone the treatment, A and the B, we'll have that A is actually more beneficial than B, right? It agrees again with this, opposed to this. Why? Because here we are actually looking at the causal structure of the system, right? Like we are consolidating and looking at the Z, right? So in essence, what we see is essentially that, you know, the condition given X is not the same as if you intervene on X. And this is in line with the famous saying that, you know, correlation is not the same, does not imply causation. This generally is known as the phenomenon of confounding. I just want to point this out again, because we're going to see this a lot of times. But a confounder is just a common cause where it's having an influence on, you know, this equality, right? Like if this is equal, then it actually doesn't make sense to call it a confounder. It would just be a common cause. But if you have this inequality, if there is a change between, you know, intervening and conditioning, right, which is very confusing to a lot of practitioners who start out in the field at first, then it actually makes sense to call it a confounder. And usually, you know, if you look at machine learning, for example, right, we have these hidden confounders. And then we think it's a bad thing, right? We generally even might think that, confounding itself is a bad thing, but it's actually not bad per se. Again, it's just a common cause which is influencing potentially the thing, right? If it's influencing it though, without you knowing about it, so again, the case of a hidden confounder, that's typically what we consider to be bad, right? Because we have something we have not considered, and obviously it's going to mess with our results and thus with our conclusions, right? So that's why we usually have this connotation of it being bad. Let's do a quick calculation here now. So how do we get, to, so I told you that, we had for the Simpsons paradox example, the reverse conclusion that, treatment A was actually better. So let's compute this quantity. Remember, Z is a confounder. It's a common cause of X and Y, and there's an error from X to Y. Now, we look first at these two quantities. So we compare for treatment A, people with small stones and large stones, right? These success rates. Then we look at the combination of these quantities. So we incorporate knowledge now on the alternative B, and we get this quantity, which is telling you that 83% approximately would get treatment A recovering in the population that we're looking at. Again, this is some kind of population, some kind of sample we have of patients. Now, this quantity is very different from the 78%, which you get if you just look at the subgroup, right? So just going back here, if we just look at the subgroup here, treatment A, 78%, that's that number. Now we can do the very same calculation, right? Just analogously for treatment B, and you get now 78% for the intervention, for the causal effect, and 83% for the condition. You will see that these numbers kind of match almost. This is just a coincidence by these numbers, right? And this example is actually, I think, taken from some kind of real data set. So that's just a coincidence, right? So don't think that these are somehow related now. And now if we compute the differences between these treatments, right, A and B, both in the conditions and interventions, we can draw some kind of conclusions, right, within the groups and within the actual causal effect. And so if we did it just for the conditions, we will get this number, right, minus 0.05, whereas we'll get the exact flip number for the causal effect. Again, this 0.05 is not so important. That's just, number play, which coincidentally is the same thing here. What's important, though, is the sign change, right? Like in this, if you just consider the purely L1 thing, you would have had the conclusion that, actually, treatment A is not good, right? But actually, treatment A is good, right? So it actually helps the recovery. That's the conclusion to draw. Another way of seeing this is actually by looking at the densities in algebraic view, right? So this inequality we have if we decompose these two statements. So if I have the causal effect and I can estimate it now with this estimand, this is not going to be the same thing as this estimand, where most crucially, the only difference is really just that we have a condition here on the Z given the treatment, which is the definition of the conditional, right? So the conditional is just defined as this, the causal effect just defined as this, and here's the difference. And so that's really a thing. Obviously, if these things become independent, then conditional and intervening is the same thing. So why did I talk about all of these things? Because, well, we are going to talk about adjustment sets now, right? In adjustment sets, we use a lot of these ideas, right? And also in the subsequent things. So for any pair XY, where Y is not part of the parents of X, right? There's no kind of weird shenanigans going on. We call the set Z an adjustment set if it can identify the causal effect, right? If we can express this causal quantity in terms of purely statistical ones, and ideally the ones we have in our data. Yes.
I have a question about this quality. What are the implicit requirements for the allowed set of interventions? Because I think only single interventions are allowed to make this sensible expression. Because in some slides you showed, for example, the intervention making X some random equal to some random distribution. But
correct.
Now we just allow for X to be in some different.
No, anything.
Anything.
That's okay. What this notation actually means. Good question, right? But this really anything. Could be random noise. It could be another function, right? Any kind of intervention is actually here allowed now. Obviously, if there's very specialist, like special kind of interventions where you're actually playing just with the parents or whatever, let's call it a soft intervention, then this thing can change, right? So I'm excluding a little bit, some of the very weird shenanigans here. But in general, this is any kind of intervention, and X can represent a set. So it can be, multiple interventions, but on the X, which obeys some kind of structure, right? And now what we're going to see is when this equivality is satisfied, actually. So this is answering your question. So here we are being very generous, right? Although it looks very simple, but now you're going to see different ways of how you can satisfy this equation. And only then you have an adjustment set.
But does this also fit the definition of the left term? I think it was introduced as a function from X to the distribution space of Y. But now we have a function on the left side and some distribution on the right side.
No, it's still a function. So if you marginalize out just the Z here, then you just have a function actually based on X, which would be in this case the conditional.
So again, the conditional is also a function.
Yes, it is. Yes, correct. Yes. Okay, so Z is now going to be similarly to this whole discussion we had on deseparation and graphical and conditional independence sets, right? Z is again going to be a set that we choose, right? And then we call it the adjustment set when it identifies our causal effect, right? And what are now ways of choosing Z? I'm going to present 3 ways of choosing Z. The first one is the parental way of choosing Z, right? So essentially, this is also related to these results that we have in Bayesian networks, where we say a variable of interest is independent of its non-descendants given its parents, right? Essentially, if you know about the parents, about the direct parents, the causal parents, which is usually the key thing that we are searching for, then we are protected, right? Then we actually identify everything because they are all the causes, right? They are everything to adjust for, essentially, to know about how, why is being generated. However, there's also 2 other ways, a bit more sophisticated, right? There's this very famous backdoor criterion where Z is chosen as a set W, where W now contains no descendants of our variable X, which we intervene upon, and it also blocks all backdoor paths. This is just now the intuitive rundown. We are going to do an example just in a second. But there's also more obscure ways of choosing adjustment. Why? Because, well, having the backdoor or having the parents is not always accessible. So what we go for can be something very special, right? But which works in our particular case. For example, this towards necessity condition is again a set W, where W contains no descendants of any node which is on a directed path from X to Y. So that's a more convoluted, more complicated concept. But if you use examples, you just boil it down, you go step by step, you write it down. It's actually very simple, right? And additionally, it blocks all non-directed paths, from X to Y. We're not going to discuss towards necessity anymore. This is just, highlighting that, you can be very specialized in the way you adjust for your causal effect. Let's talk about the backdoor criterion, just as a quick reminder from lecture 2. So here on the left-hand side, we see, 3 graphs, these special graphs, which Dave called the gifts of the gods, which is, the chain, the fork, and the collider. And we have these 3 situations, right? That, A and B are independent conditionally given C, or actually they're deseparated given C in the graph. If, you have this kind of graph, same goes for this graph. But in this graph, you're not allowed to observe C. Otherwise, they would become dependent. And by having, the global Markov property, which, relates the graphical notion of deseparation with conditional independence, but also by using something like faithfulness in the other direction, you can have this equivalence, right? Since we usually use this, you always find me talking about being this independent, although this is just deseparation. And, this implies this local factorization, right? So essentially that any joint quantity that we are looking at is really just any single quantity given its parents, right? Okay, so now the example. What is a backdoor here? We are going to show 2 examples of a backdoor and one of an invalid backdoor to also have the counter example. So we have a bit more complicated graph than we usually look at. Don't mind what this could represent. I don't have an example here. It's just, some kind of graph structure that we can analyze. And we are looking at x and y again. And remember the definition for any pair of x and y, and y is not independent of x, which is satisfied here. We say that a set Z is an adjustment set for the causal effect, if Z is a valid backdoor. And a valid backdoor here would be, for example, choosing K. Why? Because if you look here, the only real backdoor that we have is from here x over A, right, going in the reverse direction. That's why it's the backdoor. The arrow is pointing from A into X on the way to Y. So there would be a spurious association allowed through this, through the rules of deseparation and implied conditional independence. But if we observe observe the set Z to be K, containing K, then we block this node here. So there's no insight to be gained over K from X, right? And so we only remain with the direct path from X to Y. And so using the K to adjust for the causal effect is sufficient. So if you choose that to be just K, and essentially you go back to the formula that we just had, right? Here Z would be now K, then you can say that the causal effect in that specific graph of Y given the intervention X is just marginalizing out the K for this expression where you just replace now the Z with the K, right? And that would be a purely statistical thing to do, which you can estimate from data easily. You don't have to do the intervention, but you can now talk about the intervention. That's the cool thing. Another one would be a bit larger, like an actual, a set which is just not a singleton. So you include F and C now as well. You can see that, F and C don't have any business actually, with the backdoor paths. They don't do any harm. So you can add them and it will still be a valid adjustment set. Obviously, it would be a bit of a waste of a computation and somehow less optimal because you have to consider F and C. But maybe you cannot get, the conditional P, Y given X and K, but maybe you can get the one which also depends on F and C, for instance, right? So you might choose to do it that way. But it would still work, right? Like you get the same expression. It's just that, you would use different conditionals to get to them, right? And given on what you have available, this might be the better choice, right? But generally it feels, obviously, because it's more and it's more bloatware, so to say, it would be, less optimal. Now, what would be an invalid approach? We take the same set from before, but now we just add G. Now, you might be tempted to think, okay, hey, G, just like F and C, it's somehow, it's not on this path and it's also not messing with the backdoor, right? But actually, it's not a valid backdoor. If we remember the condition, W contains no descendants of X. And G is clearly a descendant of X, right? It follows on this directed path, right? So essentially, yeah?
But why is F allowed?
Huh?
Why is F allowed? Because it
Oh,
was also a descendant of X.
I might have a mistake here. I would have to check again. Sorry. I would have to check actually. I don't know. W contains no descendants of X. Yeah, you're right. According to this definition I've put here. I'll check this again and I'll correct it in the slides. Yeah.
Could we also plot this backdoor with A?
Yes. A would work perfectly fine. Correct. Yes, and essentially this is just ignore this F for the moment now, but essentially just like maybe C or something, right? You would see that it's not messing anything with the direct paths, right? But suddenly it would not work because it contains information which spuriously is associated with the causal effect. That's really the main thing behind this. Now, there's all kinds of different graphs to look at, right? So we introduced earlier in the lecture these ADMGs, right? So again, we have these bidirected dashed edges here, which represent that there's a hidden confounder. And there's all kinds of graphs, right? So if you just have this structure without this bidirected edge, we call it the frontor typically. If we have this, then it would be a confounded frontor. Here would be a conditional frontor because there's suddenly this intermediate node, which puts a condition on the mediator. But there's also some funny graphs which also got very nice names. Like, for example, this one is called a napkin graph, right? Because it's typically drawn in this fashion. And you can imagine it like being like a napkin that you can fold, essentially. Don't ask me who did this, but it kind of makes sense, at least a little bit. Yeah, this was essentially for adjustment. Yeah, and returning to our comics, now we have number 2144, which is adjusting a chair. Everyone was adjusted the chair in the past, knows that it can be a hassle sometimes. What we see here on the left-hand side, we're starting to adjust. Oh, it's going way too way back. It's going way too much up. Suddenly it makes poof, and suddenly, we have this abomination. But essentially what it's really telling you, like this comic, I think it's nice. It's a nice analogy because there's graphs, right? We can talk about all of these graphs. Some graphs are different than others in non-trivial ways. And so we can develop different kinds of adjustment sets, right? There's, the parental adjustment, which is, I guess, the easiest thing, but usually you don't get. There's the backdoor adjustment, which you could hope for getting, right? And works for a lot of basic structures. But then there's also these properties like toward necessity and much more. Now we have talked about adjustment sets, and we want to switch to the second part, right? Which is going to be truncated factorization. So just briefly, Tim was actually pointing to this earlier, that, what are the interventions that we specify, right? Most often you will actually see a concept called, perfect atomic or hard intervention. And this concept is essentially just telling you that you are fixing the value. So if I have some intervention do X, and this intervention is such that essentially there's no dependence anymore on its parents, right? It's like in a graph, you do a cut. That's what we call a hard intervention. So an example could just be, say X takes, the natural numbers as its domains, then, putting X to 4 would be a hard intervention. So whatever it depended on previously would not work anymore. Now, we talked about this class of Markovian SCMs, which is special, right? Because any causal effect is identifiable. And now we present the truncated factorization formula, which we can learn, which we can use in this subclass to do identification, right? And then by learning, we can actually estimate it. So let again B denote all the variables of some SCM, then some kind of instantiation of V, small v, and some kind of intervention little x. This causal effect is identified by this quantity on the right-hand side, which is a factorization really over the kernels only, so over all the causal mechanisms, so Vi given its parents, but with the condition actually being hidden here in the product. So we look at all the variables in our SCM, except for those that we intervened upon. Because those that we intervened upon, it will be something like, what is the probability of X being 1, given that I put it on 1? Well, that's 1, right? So 1, you can just ignore, they drop out. And so that's this formula essentially, right? And this naturally works for Markovian SCMs, which do hard interventions. Now, if you want to look at any subset Y of your variables, right? You don't want to look at all the variables, then you just get this marginalization term up here in front, right? So you look at the sum of all the variables which you have not intervened upon and which are of interest. But then the other part is just the same formula. An important thing is this consistency, right? Essentially telling you that in any situation where, you actually have what you intervene upon appearing, for example, if you look at this quantity, X being 0, although the intervention is putting it to 1, that will be inconsistent, right? So these terms are kicked out essentially. This formula, typically by Perl, it's called truncated factorization, but by other practitioners in the field who are also more related to the potential outcomes framework, they also call it the G computation or the manipulation theorem. Let's give an example, some kind of intuition with graphs. So we have here again this graph structure, which is again the same structure we saw with our kidney stone example, just with different symbols now, X, Y, and Z. We know that the joint distribution can be identified by taking the conditional of Y given X and Z, taking the conditional X given Z, and then just the prior on Z. This is just the general factorization that we can do. But through our theorem, right, the theorem which we saw for the, ignore the 2 for now here, for the adjustment set, it's just this, right? It simplifies to this quantity. So you actually just have to look at how Y is being computed by X and Z, right? And you can ignore any dependence between X and Z. And this is given, graphically, we do this do intervention. And because we place X to its value x, it doesn't depend anymore on z, right? Like I force it to be that value. So that's why we cut the graph, right? And that's exactly this formula. So this is really the intuition, right? So if you have an hard intervention, if you have a Markovian SCM, so there's no shenanigans going on with hidden confounders or so, it's a very clean setup. And essentially, this is the intuition on the graphical level. And in the formula, it looks like this for this particular graph. Okay. Now, as a final part, we want to switch to Pearl's do calculus as a means of doing proper identification, as we have phrased it. So Pearl is actually very active on Twitter, and we all follow him. And it's actually, yeah, I mean, lately, because of all the stuff going on in the world, he's originally Israeli. And so, you know, it's a bit tedious to follow. But for all the scientific content, I think it's a lot of fun. Especially, you know, when he's preaching the causal calculus. So here we see Andrew Heiss, naive question. Are backdoor and front door adjustment? We have seen backdoor, right? Remember, we are blocking the backdoor paths, right? No descendants, blah, 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 and so on. And front door adjustment, we haven't seen. We have just seen a front door graph, but there's, again, you know, a special formula just for that. Are backdoor and front door adjustments in DAX just specific applications of the 3 rules of do calculus? Or are they actually a separate thing, right? Clearly a question to Pearl, who devised this do calculus. And yeah, Pearl actually answered, right? Naive questions are everyone's questions, appealing to the people, of course. The answer, well, the backdoor and the front door are logical consequences of the do calculus. You can see so also if you boil down the historic development, you know, so I mean, Euler Pearl devised the Bayesian networks, had his book on heuristics in the 80s, and then, you know, slowly but surely in the 90s, he developed essentially this do calculus with all these notions related to d-separations and so on. And so it was really actually quite literally a logical consequence because he was using logic to you know, come up with these things. And yeah, so he's saying, why do we decorate them with names? Because they're easily recognizable, right? So that's the only justification, right? So we store them in our toolbox, right? And if we see, oh, this is a backdoor structure, let me use the backdoor formula. You don't need to do the do calculus. You don't know yet what the do calculus is, so you're going to see in a second, right? And then you're actually going to understand why you also don't want to use it, because it's a very general tool, which can do everything, which would be tempting to say, yeah, let's do that. But then again, it's a general tool, so it's more expressive, more powerful, and more complicated. So you don't want to use it, right? So if I know my problem is easy, let's use the easy tool, right? Don't overkill it, right? Like imagine in a video game or something, right? Like you are level 60 now with your character, right? And there's a character which is level 5, right? Like if you use your strong attacks, this thing is going to be obliterated, right? But so, you know, you might just opt to, you know, saving a little bit of your mana and, you know, going with the small attack. Yeah? Anyhow, so identifying literally anything, right? So we have seen that the Markovian SCMs can, you know, be identified in any case, but there's also non-Markovian SCMs which don't allow for everything to be identified. The do calculus has been proven, we are not going to prove this here, but it has been proven in the 90s to be complete. So anything which is identifiable, even in the non-Markovian case, you can get your estimates, right? So how does the theorem go? So for disjoint variable sets, X, Y, Z, and W, so here we are using 4 sets even now, you're going to see why, we have 3 rules. The first rule is going to be the invariance to observation. So what does that mean? Essentially, if we have this causal effect, which is, you know, somewhere on the spectrum between an intervention and a counterfactual quantity, because, you know, we have this condition set an X extra to the intervention, we can simply drop the X here if this condition is satisfied. What is this condition? Well, it's first just the conditional independence condition, which, you know, we can use DH-sig, as we have seen, you know, in lecture 2, for instance, to test for this with our data, right? But, you know, this is actually a graphical algebraic tool, right? So that's why, you know, it's a proper framework of Pearl's graphical models. And so this is actually a d-separation statement, right? So a d-separation statement where you can just look in the graph. So it's even easier. And you can look in this graph. This graph is a little bit different. So this star in front of the W is indicating that incoming arrows into W are all being deleted. If I were to write the star behind, then it would be all the outgoing arrows, right? So if we remember earlier the graph, for example, where we had, the x, a, and k and y, for instance, a was pointing into x, and if I have now a star x, that would mean that, I would remove that edge from the a. And essentially, if this is satisfied in the graph, which I can easily check, then I have this invariance to observation, right? So I can just, whether I have this condition x in here or not, doesn't matter, right? So it's an invariance, right? I can just ignore it. Now, there's also a second rule which states an invariance on the interventional level. So what do you expect here? Well, you expect the same game here. We have x here again, but x is now an intervention, actually. I can just ignore the intervention. So it's a very powerful thing. Like, when can I ignore interventions? Before, I could ignore conditions, but now I can ignore interventions. It's when this condition in the graph is satisfied, right? Where now you see it's a bit more complicated. So we are deleting incoming edges on W and outgoing edges on X. We are not going to dissect, the intuition behind any of these rules now. We're going to do one rule, just for an example, but not the whole picture, and we're also not going to prove it, right? So bear with me. Now, rule 3 would be an equivalence. It's a very useful tool once again. So before, we could just, drop things or add things, if that actually helps. And here now we can exchange things. So we have a bridge now between observations and interventions. So here you have, again, the dual x. But here now it's not being dropped, it's actually the x, which you keep. So you're just switching the disguise, right? And again, all of these are equalities, right? So I can take away, I can introduce, I can take away, I can introduce, I can switch, right? And here it will be on this thing, right? Okay, so now let's do an example. Let's take the confounded front door graph, which we have seen before. So we are interested again in the causal effect of x on y. And we used our graph as an assumption. And just by using the axioms of probability now, we're going to do now derivation using the do calculus. The do calculus is just an extra tool. We still use all of our, base rules and, axioms of probability theory. Here, what we can do is we can just decompose in the following way. So we have this front door. So we know that, we can express y also as this quantity, given, the intervention and, the condition on m. And m conditioned on the fact that we intervened on x, and we marginalize out the m, right? So essentially, if you get these together, this would be a probability of y m given to x, and since you sum out the m, you would just have the y to x. So it's clear to see how this leads to this equation here. Now, in the next step, we use rule 2, right? So I'm not going to actually point to all of these things now in the interest of time, but rule 2, again, was just ignoring the interventions, right? Or actually adding interventions, right? So the invariance to interventions. So what we are doing here is now, actually, this should be rule 3, right? Like we are changing from the condition to the intervention. But this is what we can do. We can introduce the intervention here. It would not be any harm. Everything is being kept the same. Now, again, it's consistent. As you can see now, it's rule 3 now from the previous slide. You have written rule 2. But again, we are changing. We are saying, okay, this is now condition instead of intervention. It's satisfied in the graph where we, cut these ingoing, outgoing edges. And now here, what we do is, which is rule 2 from the previous slide, we remove, I'm going to correct this, by the way, in the post edit also for the recording. The do x, is being dropped simply, right? So here we have the invariance to intervention, right? Coming from rule 2 from before. And here in these two, we use the do calculus to switch between intervention and condition. In the above, we just use the axioms of probability. Now, this derivation can go a little bit long, but you can play the game. And essentially, you end up with this formula. Looks very complicated. You would think now, oh, why didn't I stop here, for example? Well, our goal was essentially to just get rid of the do. The do is a causal quantity, right? So intervention, counterfactual is a causal quantity. And in identification, again, we said we want to just express it with observational quantities. Observational quantities are the ones which don't have the do. Very simple Eselsbrücke, right? And so, for example, also for the exam, if you don't want to justify anything, just remember, get the do out. That's all you want to do, yeah? Pun intended. And then here, right, you have really this thing, right, which has no do's anymore. And it's following the rules the rules are complete and have proven to be also sound. So any conclusion will be valid as long as you apply the rules correctly. And so we can be sure that this innocent quantity, the causal effect in this graph, is this, well, more complicated quantity, but at least we can actually get this one opposed to this one, right? And so here you have an example derivation really showing you how you apply the do calculus. And also, so for anyone who actually wants to try out the do calculus themselves, again, it's not just that you apply the rules of the do calculus, it's actually also, you know, anything you know from probability theory. You have to use everything. Otherwise, you will not be able to get the estimates. And also, sometimes you will have to apply a certain rule multiple times, maybe even to the same argument, to come into an algebraic situation where you can then apply another rule. It's very much an algebra game, right? So it's like back in high school, you know, the task is, you know, you have this equation simplify, right? And then, you know, somehow you have to think and figure out how you simplify it, right? That's essentially the game you're playing here. But now let's do an example of actually how we explain and how we interpret one of these rules. So invariance to observation, this was the first rule we saw. And in this rule, again, I've written it down here, right? So incoming edges to W are deleted. We check for this deseparation statement. And if that's satisfied, then we can do a transformation like this, right? Like we can kick out a condition or add a condition. Now, in red, I've highlighted you now the sets as they are depicted in the rule, but they need to be chosen now here. We are going to choose them for this graph. It might look a little bit confusing because we're using the same symbols here. I should have maybe put like A, B, C, D or something, right? So it makes it easier. I guess I'll do it also for the post-edit. But essentially, you know, the X, which is red here, is chosen as the Z here, the Y as the Y, the Z as the W, and the W as the X, right? It's a bit ridiculous, but this is what you see a lot in causality, actually, especially in identification. Okay, so we have this graph. Now what we do is, right, so this is the notation that we use here. So we are cutting the W's, right, which in this case here is X. So we are, so bear with me, yeah. Essentially, this is just denoted here by highlighting that these nodes are gray. And then, you know, we end up with this thing. And this thing is actually what, yeah, comes out of applying our rule one essentially, right? So we have Y just being dependent on X and W here. This is the only thing you have to look at, right? So in this thing, the deseparation statement that, you know, Y is independent of Z is satisfied naturally, because Z is not appearing anymore here. I mean, it's here, but it's separate. I'll revise this example once more. Yeah, sorry. Okay, now switching to a final topic, right? So as you might remember from section 2, we have seen that there is, you know, these three ways of adjustment, truncated factorization, and do calculus. But I also mentioned something about optimization. And optimization comes into play when we do partial identification. So far we have seen the problem of identification, so expressing any causal quantity in terms of, you know, purely statistical ones. And we got exact results. So any equality you saw, anything on the causal effect was exact, right? Like you get the distribution, or you know, you get a numerical value at least, whatever. But what if you cannot get it exactly, right? Like what if, you know, I have a treatment and I cannot estimate, you know, that it's going to be, I don't know, 23 percentage points helpful for recovery or something. Maybe I can at least say that it's going to be positive, right? It's going to be greater than 0. Can it maybe be greater than 10? Whatever the value is, right? That's actually what we mean by partial identification. So it's a very, very important, especially practically important topic. And so given that it's not a true identification in that sense, it's just, well, partial identification, it's a sub-problem, it's a relaxed problem. I've kept it here separate, right? But this is what we mean by optimization. And just briefly, I'm going to give some intuition. So regular identification requires that our conditions, such as, you know, causal sufficiency, that there are no hidden confounders, are met. But this is typically not the case, right? Like there will always probably be some kind of hidden confounders that we cannot, you know, adjust for. And that's also the thing, right? Like we talked about adjustment, but, you know, if there's hidden variables, if there's actually variables that you don't even know about, then you cannot possibly adjust for them, right? And Now let's take the medical example. The medical doctor, right, would be very happy actually to just know that a drug is positive. Like if the drug is guaranteed, that's the thing, it's a guarantee, right? Like if the drug is guaranteed to have a positive causal effect, then you can just give it to the person and you're safe because you know like it's going to have a positive effect, even if it doesn't end up helping, unfortunately, right? So a medical doctor is totally happy with that, right? And given all the hidden confounders, you could never hope for proper identification, right? But maybe for partial identification, because we just need less assumptions, right? So in essence, it's a discussion of qualitative versus quantitative insight, right? And more than not, we are happy or we actually endorse the qualitative insight. So let's give an intuition. Here we have a graph again, a bit with color now. So we have Z, X, Y, and Z. Z is here now the treatment, which is going to be assigned, right? So decision, for example, treatment A or B or something. And then treatment X is actually the thing you actually receive. Don't worry about this interpretation for the moment. This is just for the sake of the example now. It's going to be easy to understand here. Now there's some kind of measured confounder, right? For example, you know, the kidney stone size essentially, which will dictate whether they actually get a certain treatment. And then there's some observed response, right? Whether they recover. But as we said, more than not, in the real world, the C is actually U. It's an unmeasured confounder. We don't know about this. We don't know what the doctor is thinking when they're actually administering then the treatment, or how you could also interpret this as some you know, doctor actually deciding which treatment you get, but then maybe the nurse actually mixes up what treatment you actually receive, right? So this is realistic ways of looking at this. Now, we just need one concept before we can, you know, actually discuss our example. If we look at our exogenous terms, right, especially if we imagine now our exogenous variables being some kind of categorical domain, right, like say, you know, numerical, let's say binary, for instance, right, then essentially you have a function, right, say, you know, Z is just a function of some exogenous variable, uz, and uz has its domain being 0 and 1. Then really your function is two functions. It's one function for uz being 0 and one function for uz being 1, right? So essentially these are the so-called response variable functions. So we have these so-called enumerable, right? So we can count them, function sets, right? For any structural equation. So formally we write it down as this: let Rv be a variable where the value, the domain, is set as the natural numbers up to some number nv, and nv is just going to be the size of that variable, right, or its domain, to the power of the size of the parents, right, like the number of the parents. So if we do our example, it would be, you know, if say, you know, z is a binary variable 0, 1, and uz is also a binary variable, then you would have here 0, 1, the cardinality, that would be 2 to the power of the size of the parents, which is 1. So 2 to the power of 1 is 2. So we would count 1 and 2. So the response variable function would be 1 and 2 in its domain, which indicates that there's two different functions, how we can actually compute Z from its exogenous terms. This thing is just a purely, you know, algebraic construct, which we call the response function variable. Why do we do this construct? Because there is this very awesome theorem that essentially you can use this construct, right, to express the observational distribution. So the observational distribution of some SEM, PV, can be simply rewritten as this quantity, where you have the probability of any of these response function variables, right, the actual value, times this product here, which looks a little bit complicated, but which is just telling you it's an indicator function of whether the observation that you want to, you know, compute now is consistent actually with that response variable function, with all the ones actually. So to give an example here, let's convert first our exogenous terms now to these RFVs. So for Z, we will have this one here. It's just going to be 2 because we do binary, either treatment is assigned or not, and there's two different functions. For X now, right, we have two parents. We have Z and U in this case. So it's going to be 2 to the power of 2, so 4. And for Y, the same thing, just that it's X and U now. And now we can rewrite the joint distribution, Z, X, and Y, in terms of these response variable functions, Rz, Rx, and Ry, given the structure, in the following way. So we have some observed data, right, or at least something we want to, you know, estimate, PV. And here we have the formula from before. And what could be an example? So V could be just, you know, someone say if this is ZXY, then Z0. So they get treatment 0 assigned, but actually they end up with treatment 1, but they actually recover, right? And so you have this situation, for example, that you want to model. And now our condition here, this indicator function, is just looking at all the states which are consistent with this. Here I'm actually not showing any numbers, so you cannot verify any of this for the moment now, but this would be actually consistent, right? So it's really just the sum over all these different probabilities which talk about our response variable functions. So the R bold here is just indicating that it's like for Z, X, Y simultaneously, just in vector notation, right, or set notation. So this is what we are doing. Essentially, we have this graph. We decompose our exogenous terms in these response variable functions, and then we have this constraint satisfied. And now, crucially, and that's the cool part where we get now to partial identification and optimization, actually, this thing on the right-hand side, well, these are just linear equations, right? You can actually see them as a system of linear equations, depending on what example you're looking at. And so we can actually use linear programs, right? So linear programs, if you remember from, you know, mathematical optimization, they are the base class where we have linear constraints, linear cost function and linear constraints. And we are trying to find an X which optimizes our cost function such that it satisfies the constraints that we pose on it, you know, and, you know, X, for example, needs to be positive for that. And that's just a mathematical notation. So an example for this could be something like a shortest path problem or an assignment problem, right? Or the diet problem. For example, you want to figure out what's the best diet for this semester, right? Like, what are the foods you want to eat, right? Like, you want to have some pleasure by eating pizza, but you also should be healthy, so you got to eat more greens, right? So your X would be all the different amounts of how you choose those, right? And the cost function would be, you know, pizza, for example, oh, it's very, you know, I don't know, calorie dense, for instance, right? You're optimizing maybe for your weight or whatever, right? So this would have a high cost of eating, right? So you cannot eat that much pizza. Salad, for instance, very, very low in calories, as long as you don't have very fatty dressing, yeah? And then that could, you know, you could have a lot more, right? And then the constraint would be, for example, that say you cannot eat that much salad because of whatever, right? You just start puking or so. So there's a restriction on that and so on and so forth. That's just a linear program essentially. And now we can use these things because we have these linear constraints that we saw from the previous slide to actually find out something about our quantity of interest. As we saw at the very beginning of this class, you know, our desired quantity, you know, is some kind of causal effect derived from the, say, interventional distribution. It could be the average treatment effect. And now we want to know the average treatment effect of a drug, and we want to know it qualitatively, right? We want to know, is the certain drug that we take, drug A, is there a positive causal effect, for instance, right? And now, by actually framing what we saw earlier with the response variable functions as linear programs, we can get bounds. We can get like, oh, you know, in the worst case, our causal effect is going to be this, and in the best case, it's going to be this, right? And this optimization is really just being performed by LPs. Yes. Yeah, because of these things, essentially. You have here these linear constraints that you can pose.
Sure, but you still have the graphical model.
Mm-hmm.
Yeah, graphical models are not linear programs.
They are not, but they are the assumptions you make, right?
So that's what I'm asking.
Oh, you're asking. Oh, you're asking. Why do you get the guarantee then, or what?
But you now tell me that I can do inference in this joint system. Let's call it like that for the moment, in polynomial time. So we went from NP hard to polynomial, which is cool.
No.
Or does it mean that you now get, for example, bounds that are trivial potentially because it's 0, 1? So where do you change the complexity stuff? Which assumption? Because in the graphical model you're showing, you still have potentially loops and so on, right? Because you get the dependencies even on the function side. Or is the assumption that the Bayesian network part is always a tree, or I don't know.
I would have to check. I think the assumption is definitely that they are DAGs, right? Which is still a more general class than trees, but
Bayesian network is sharply from tree.
yes. So can you repeat your argument? Maybe I can find.
I don't know. I don't have an argument. I'm just saying a Bayesian network, and because of that, also for me, causal models are sharply complete.
That's true. Yeah, that's. I mean, the proof by Cooper and these others. Yeah.
Magic, we get linear programs. And linear programs are polynomial. I mean, we don't know the degree, but it's definitely.
Sure. So we are saying, okay.
Where's this? Where's finally the
I think it's the number of constraints we get by iterating over all the different combinations we could possibly get by these value functions.
I think I know what's happening. I would have to check, right? But my intuition is the following. When we say sharply complete, right? We are talking about, say, something like marginal inference, right? Which makes a lot of sense. We have the semantic graph, not like in an SP and a computational graph, right? We have to go over all these exponential variables. So that's where we end up. We even have to count the words, right? So it's sharp P, not even NP. And you can derive with this the causal effect. But here it's just partial identification, right? So we are just getting the bound. So we are not even getting the actual estimate. We don't even have to, no, we don't even have to count, right?
For epsilon, approximate inference is also NPR. So
Yeah, that's true actually. Yeah, that's true. Yeah. Yeah, that's true. That's true. That doesn't work.
But let's check. And it's not like I don't want to say something wrong. I think that's interesting to see what is happening. The second part is we could maybe better or mathematically then make use here now of our idea of if you apply to this LP the idea that an LP and explanations in LPs have also a connection to causality. What would that now mean? So if we look at our recent paper, isn't that not interesting? And so maybe we can build the hierarchy both in terms of attacking, so just background. Everyone is talking about adversarial examples and how brittle deep neural networks are, but actually linear programs are all the same. I mean, everyone is attackable. And so I think it's interesting to also attack this LP here and showing that you can get easily different estimates, and we may even control when to get the different estimate or the different bound. So I think that's interesting. And then what Matai and the whole research was showing is that this is related to if you have the true model at least in mind, the true causal model, then you cannot affect the LP that you use. And so then we can maybe also make that point here.
No, it's very important. I mean, I'll check and I'll actually provide everyone then in the upcoming lecture with, I guess, the post edit. The thing is, I was just thinking whether, because what you optimize here then is, for example, the ATE, which you put in your CTX here. And it's definitely sitting on the level somehow lower from complexity than the graph.
The LP has to vary the remaining part of the graphical model. And this is where
and I think that
So what I want to say is maybe I misinterpreted. You know, maybe
no, I was just not
but maybe no one is saying that this LP is easy fixed, right? But I would argue it's then not an LP. It's only an LP if we abstract from the graphical model. When you have to solve the LP, it becomes a piece. That's.
I'll check it. I'll check it once more. This is also That's the thing. I have to check this once more. I'm not sure myself right now. I mean, you have on the algebraic level, you have just this thing, right? But then again, I don't know whether it's just assumed whether you actually have these values, right? Like I have to check. I think so, which would, I think, again, also make this easier. But I think we are really on one level below in the hierarchy of, like, you know, okay, these are just, you know, the expressions, and now this is actually the model size, right? Which would help resolving this issue which we just discussed with Christian. But I'll check this once more. I'll do a detailed example. I mean, it's not that important, right? So that's why but I wanted, for completeness sake, actually to mention it, right? And this is the rough idea behind it, essentially. That really you end up with these kind of things, right? Instead of saying, like before in our example, we had 83% were surviving if they get treatment A. And now you're saying, well, it's somewhere in this range, right? Like we could say maybe it's just like a 50% increase, right? Or maybe it's even more than what it actually is, right? But we definitely know, for instance, here it's non-zero and it's positive actually, right? What's interesting is when these intervals end up being at the 0 point, say one of them is negative and one is positive, right? Then you're kind of screwed, right? Because you cannot conclude anything, right? Because in the worst case, actually the drug has a negative effect, right? So that's what physicians hate the most. But yeah, we'll check that once again. But with this, we are actually also on time, I think. Here's the end. One more final XKCD, actually for linear program or for generalization of that, the traveling salesman problem. So we are just talking about complexity. So I think that's quite funny that we have this here. So you see, you know, the traveling salesman going all over these places, right? And, you know, trying to sell their products. And well, it's very complicated, right? It's factorial here. And now we can be smarter and we get this exponential term only, right? It's not that bad, although it's still bad. But see, going on eBay, you can actually just be, you know, yeah, 01. And I leave it with that. Thanks again, everyone. Just one more announcement. I guess no one has any questions now. Again, some of these things are fixed, right? That we got pointed out. For example, what we saw with the backdoor, or what we saw with just now, like having a more detailed example to understand properly. But next week, however, is going to be mainly the coding tutorial. So please, everyone, bring your laptops, right? Everyone who you know will be attending who was not here today, tell them as well to bring the laptop. Obviously, we're going to announce it as well, and we're going to share everything also, I guess, a little bit in advance. But yeah, the coding tutorial is really, it's a lot of fun. We have done it at several, summer schools, and everyone has loved it. So I think you're really going to appreciate the concepts. It's like with a storyline, and you're, playing through the storyline. Sometimes you have to change something. Sometimes you don't need to change anything, and just, think about it a little bit and click on solution. So there's both of these dimensions, and we are covering essentially everything we've done, right? Like the causal hierarchy, the discovery part, identification from today, everything. Yeah. So look forward to it. Yeah.
Hello, everyone. This is Mate speaking, post-lecture. So this is a recording of me after we have had the lecture, just to correct some of these things which were incorrect or insufficient or non-optimal during the lecture. So let's jump right into this. I'll append this at the end of the original recording so that we also have the original. I guess that puts it into better context. Yeah, so the lecture was on causal identification, and I'll just jump to the slides that we want to discuss about for the post-recording correction. So the first correction we're going to make was on this slide. Actually, the set that we are presenting here, the Z, which includes F, C, and K, was a valid adjustment set indeed. It was just not a backdoor. So that was just my mistake. So here we see that we have a valid backdoor if the set is just a singleton K, because there's no descendants of X in that set, and also we are blocking all the backdoor path. There's only one, which is going via A. Now, if we add F and C to that set Z, we don't have a backdoor set anymore, as was pointed out from a student, totally correct, since, F marked here as red is actually a descendant of X. So that would not be a backdoor criterion. However, I actually had this example because for completeness, it shows you also the third option, which we presented, the towards necessity one, which is still a valid adjustment set. So we still have the equality between our decomposed statistical terms and our causal effect. Just that it's not a backdoor, but a towards necessity condition. So if we just jump back to the slides where we defined it. So we have Z being some set W, which contains no descendants of any node on a directed path from X to Y, and additionally blocks all non-directed paths from X to Y. So we certainly see that F, C, K are blocking all these non-directed paths. And now if you look at the directed path from X to Y, you know, we have D in between. And so, you know, G would be problematic. Obviously, D would be problematic. But F is not a descendant of any node on that directed path, actually. So that is a totally valid adjustment set according to our conditions. It's just not a backdoor set. So that's what being pointed out here now on this slide. Now, just briefly, here I've adapted the slide a little bit. So essentially what we're just saying is that our random variable x, which we intervene upon, will be set by some function g, which can have some argument. It could also just be a constant function. And as long as it cuts off the parental dependency, right? So g is not a function of the original parents of x, nor for that matter of any other new parents, then we call this a hard intervention. And the example would be typically, you know, a constant function, for example, g being now the value 4 here. Obviously, x needs to have a domain which covers, you know, the value 4. But then, you know, do x equal 4, we fix the value to 4, and that would be a hard intervention. Let's jump further ahead. So for the do calculus, I've just cleaned up here a little bit. So you see we have here the graph in which we check the D separation where incoming edges are deleted. Here it's incoming and outgoing edges for 2 different node sets. And here actually, I didn't mention this in the original lecture, but x of z is the set of nodes x that are not ancestors of any node of z. In this case, then the graph where the incoming edges to W have been removed already, right? So it's a sequential operation here. Other than that, here for the examples, I've just corrected. So here now it's in line with how we defined the rules. So here we're applying rule 3, once again, rule 3. So we have this equivalence between observation and action. And then rule 2, because we can just ignore it, an action, and so on and so forth. Okay, and let's jump now to the final part, which was, or the penultimate part. So we also explained the rules. Here I've just adapted the example. Instead of using the x, y, z, and w within the graph as well, I've opted for A, B, C, D. And we still have the way you know, our red set from the rules are being set up. So x is just a singleton B, y is D, z is C, and w is A. Now what we do first is just remove the incoming edges to A, because that's the one that we want to get rid of, essentially, because this invariance to observation. And in this new graph now, we will observe A and C and check for the D separation statement. And we see that indeed B and D are independent. And so we can conclude that our rule works. And our rule will now tell us that the probability of D under the intervention A and the condition C and B is the same when we just drop the condition B and keep everything else the same. Okay. Now this covers also the do calculus. And finally, we'll have, yeah, I guess the big bulk, which we had at the end, a discussion also with Professor Christian Kersting, where we talked about partial identification, specifically about, you know, this linear program setup. So let's just go over it quickly once more in full detail. So the motivation is simple. I mean, we have partial knowledge, right? So regular identification requires conditions, you know, such as causal sufficiency. So there's no hidden confounders, but this is virtually never the case. And, you know, from a real world inspired standpoint, you know, any medical doctor, any physician would be more than happy to actually know the causal effect of a particular drug, to know that it's certainly positive and I cannot do any harm, right? So this is this qualitative versus quantitative insight. So that's kind of the motivation. And it's dearly inspired by the fact that usually we are not in a perfect scenario. Another thing would be to say that, you know, you run a medical trial and not everyone is actually complying with the setup you have. And obviously this would endanger the causal inference you perform. Yeah, here we just had this example, right? So, you know, there's some treatment assignment, but then what actually happens with the treatment, whether it's taken or not, is dictated down the road. And there's a hidden confounder at that level. And then we have this observed response. But in reality, the confounder, at least, is usually hidden. And now we defined this important concept of this partition of this response function variable, RFV. And I've corrected here the definition to make it a bit more precise. So essentially how the domain is defined. It's just the natural numbers up to this NV, and this NV is really a number which is calculated from looking at this exponential term, which is the size of the domain of the variable. For example, if it's binary, this would be 2, and then to the power of the product of the size of the domains of each of the parents. Sounds a little bit complicated, but it's not. We are going to see in just a moment. Other than that, the theorem stands as before, right? So the observational distribution can now actually be rewritten in terms of this partition. So I'll go now on the extra slides that I've prepared. I mean, here it stands, right? But you'll see in a second. So here, these are the new slides. Also, just as a quick reminder, none of these calculations as such are actually important for the exam or any such thing. It's really just for the educational purpose. And I mean, sure, it's important to know the general idea and the setup, but nothing else for that matter. I mean, it's anyhow, even within causality, which might be considered a niche topic still, within the greater scheme of AI, it's still a niche within the niche. So here we have this partition illustrated as done in Pearl's original book, which I also reference. Here we essentially just state that if we have two, say, binary random variables x and y, it's very easy to show with binary variables, then there's really just 4 situations our function for computing y can actually have. Essentially, the function can always just ignore the input and then just, produce either y equals 1 or y equals 0, or it could, match the arguments somehow, either by having them both be equal or being unequal. And these are the so-called equivalence classes, right? Now, we had our previous graph, right? It's the same graph here again, but now we want to compute these RFVs. And for example, if we look at Z, Z has domain 2, has no parent in here except for the exogenous, but those we don't count in the formula. So that will be 0, but because this is the base case, so it's 2 to the power 1, it's 2. So the size would be 2. We have 0 and 1. For x now, it's different because we actually have a parent, z. So it's 2 to the power of the domain of z, which is 2. So 2 to the power of 2, which is 4. And then we have the same game for y. Now, if we look at the graph again, we might be interested in something like the average treatment effect of a drug, right? So the treatment and how it affects our observed response. And generally, in the binary case, we can write it as follows. So we have the probability of y being equal to 1 in the difference of doing or not doing the treatment, right? So do x1 once and do x0 once, right? And we just subtract those. And for this particular graph, and since the variables are binary, we actually get the formula we have had from the Bechdel adjustment, which is just adjusting for u in this case. So it would be a sum over these conditionals where we marginalize out the u, or we actually take the expectation of u here. Now, if we consider the RFVs, so why did we do those? Well, because we can actually rewrite now the AT. We have seen this also in the original lecture. This is kind of these linear terms, just a bit more precise now. So if we assume the function to decompose like on the left-hand side, so we have these 8 different these 1, 2, 3, 4, 5, 6 different cases, right? Depending on what value ry takes and what value x takes. So y0 just denotes y taking the value 0, etc. And now if we look at the ATE, what we see is actually for the more detailed example, actually consider chapter 8.2 in Pearl's second edition of Causality. But really where it boils down to for this graph with these RFVs and binary variables, that the AT is really just the difference between the response variable being 1 or 2. And this actually comes about because if we look at y1 do x1, then this is actually just a sum of the 2 probabilities of ry being either 1 or 3. And for the x0 case in the intervention, it's 2, 3. And now if we take the difference there, then we just end up with ry1 minus ry2. Now, for notational brevity, because you'll see this otherwise becomes very much out of hand, we introduce these shorthands. So the probability of y being A, X being B, and given that C has been observed to be C, it's just written as PABC. So if we write something like P000, then we are asking for the probability of not recovering and not having taken the treatment after we know that there has actually been an assigned no assigned treatment, right? So that's what this would mean. It's just a shorthand. It's just notational brevity, and we do so analogously for Q, where Q is just representing now these response function variables. So X and Y in this case, because these are the only ones we care about for the ATE. So we don't need to use RZ. And now the ATE, because we know actually how it looks like in terms of response function variables from the previous slides. Remember, it's just RY, and the difference of, if you just go back, RY1 and RY2. Now we can rewrite it in terms of the Qs actually. And so what you'll see is here we have 4 terms before the subtraction and 4 terms after the minus symbol. And why is it 4 terms? Well, the second sub-index indicates the y. So y is 1 in the first case and y is 2 in the second case. And then we actually just marginalize out x. So we take all of the different values, which is 4 values. So 0, 1, 2, and 3. And so that's why you have 4 of these Q terms summed together, which essentially just boils down then to Q1, which, well, would then mean probability of RY being 1. And so you have that for 1 and 2. And so that's the linear combination here. Now, the probabilities, they satisfy some constraints as well, if we look at them from the Q perspective. For example, the P000 is actually just a sum over the 4 different combinations of taking the Qs. And this can be done actually for all the other ones as well, for all the other combinations of ABC and JK. And then we actually end up with a matrix. And with this matrix now, we can actually concretize our linear program. So how does our linear program that we talked about during the lecture now look like? Well, we are minimizing the ATE. So what you're seeing above is just copied from the previous slide. It's the ATE in terms of these RFVs. And it's subject to the constraint, obviously, that, you know, these probabilities sum up to 1 and that they are non-degenerate. But now, most importantly, that P equals RQ, where the R is now this constraint matrix, right? The set of these linear equations, essentially, where any PABC is specified as a linear combination of the Qs. This is our linear program, and this is what we're optimizing. And the cool thing is now that when we solve this linear program, as promised, we get these bounds. Here we can actually do it analytically for this binary problem. So that's why we don't have to specify parameters for the actual probabilities. But yeah, you get upper and lower bound. For example, the upper bound would be something like that the ATE is bounded by the minimum of the set on the right-hand side, which here is abbreviated, but I'm just showing 2, for example, that, for instance, 1 minus the probability of y being 0, x being 1, z being 1, minus probability of y being 1, x being 0, and z being 0, and so on and so forth. There's actually about, I think, I don't know, almost like 10 of these constraints, and they don't all look exactly like this. So I recommend checking out the more detailed example as referenced earlier. But essentially, you have the set of these different quantities, which are all uniquely determined as soon as you actually have some parameters for probabilities, and you just take the minimum out of that one. And that value will then actually be the upper bound for the AT. And just as an analog, you do the same thing now for the lower bound, just that you have a greater equals on the max of a different set of these constraints. Now, when we talked to Christian was correctly noting that, well, we know Bayesian networks have a problem with inference. That's where all the discussion around, you know, probabilistic circuits like some product networks came about. They are very nice in that they are semantic graphs, but they are not computation graphs, therefore, and they are very inefficient. So it has been known since a long time, results by Cooper and others, that exact marginal inference is actually sharp P hard, which is even worse than NP hard, and even just approximate marginal inference is NP hard. And since SEMs actually inherit, this has been actually a work from our lab, since SEMs inherit from BNs that semantic nature, causal inference in SEMs is consequently also NP hard, even on an approximate level. Now, this is what Christian had in mind, right? So when we talk about inference, when we talk about Bayesian networks, it's always this exponential lurking around, and that makes things, NP and sharp P and so on hard. So very horrible computational classes. And when we think now about linear programs, well, they are somehow polynomial. It doesn't matter how big the polynomial is, but qualitatively they don't grow as fast. Well, Christian had a right hunch. We are not solving this problem. I mean, now looking into more detail, we actually see that this term where we compute the states of our RFVs, it's actually super exponential, right? Like it's not just exponential, it's super exponential, and it's growing with the number of variables. So when you take this term, which is the product of, for each of the parents, the size of its domain, let's say we had another variable now, let's call it Q for the moment, and Q would be a child of Y and X from our previous example, right? Remember, X had now a domain of size 4, right? 0 to 3, or 1 to 4, however you want to specify it. Same went for Y. But now our Q, well, it's still binary variables, so it's 2 to the power of something, but this something has changed now because the domain of our parents, they are both 2 each, right? So we have 0, 1 for X and Y still. But now we have, well, these 2 parents appearing here, and we're taking the product. So it's 2 to the power of 2 times 2, which is 2 to the power of 4, which in this case would be 16, right? And now if you look at the whole model, then we would have to take these domains. We would have like 2 times 4 times 4 times 16, and that's already super large just for 4 variables. So we quickly see that, we are not circumventing anything. The LP is still of polynomial nature, but because of the super exponential growth through the variables, we essentially suffer the same fate as causal Bayesian network when it comes to inference. Just to put it in a more like computational complexity class perspective, there's this existential time hypothesis, which looks at 3 SAT, the satisfiability of these conditions where we have 3 lateral combinations, and that requires exponential time, c to the power of m for some constant c greater than 1, and m being the number of variables, so the thing that scales. And the hypothesis essentially implies that any NP-complete problem requires time c to the power of n to the power of a, where c is again greater than 1, but a is just required to be greater than 0. And we clearly see that our partial identification procedure, VLPs, falls into this category, right? So essentially, we have not gained anything on that side. However, there is actually a silver lining. So while we did not gain on speed, right? So inference is still really hard. That was actually not the goal, right? Remember our motivation? It was about partial knowledge, right? Or the fact that we do a medical trial and our patients might not necessarily comply. And in this case, what PI allows us to do is still get a correct causal estimate, not a point estimate, but at least an interval. It might not be tight, right? So it might still be bad. But even if it's a loose bound, as long as it's, say, just in the positive domain, we could conclude qualitatively that the causal effect's positive, always, whether it's the worst case, the best case, right? So and we did so by just taking a minimal set of assumptions. And now this is the key part, right? Like we don't gain on speed, we gain off the number of assumptions, in the sense that we don't have to make as many assumptions as for, getting the point estimate. And doing less assumptions is more realistic. And so that's the awesome part. And yeah, with this, we are again at the end, actually, now also of the post-recording edit that I've done here with you. Again, we have our traveling salesman problem. And again, the guy is now going to eBay to just reduce the complexity. Thanks again for listening, and See you soon again. Bye-bye.